Hello, this is the section 3.4 lesson. In this section we're going to introduce an extremely important type of distribution called the normal distribution. So we're going to start off here by defining kind of a special case of the normal distribution called the standard normal distribution. So a continuous random variable z has a standard normal distribution if its PDF is given by this function right here. So 1 over square root of 2 pi. Now pi here is really the number 3.14 e to the negative z squared divided by 2, and for z between negative infinity and positive infinity. Okay. Now note here that we use the letter z to denote this random variable, and we're going to reserve that letter z to denote a random variable with standard normal distribution. So whenever you see a random variable z, that's going to imply that it has a standard normal distribution. Now here's the graph of this density function. Notice that it's got this nice bell curve shape. Notice that 0 is right in the middle. It's symmetric with respect to the vertical axis, which means the area under the left half is 1/2 and the area under the right half is 1/2. Notice that there's a lot of area right around z equals 0. Not much area out here to the left of -2 or to the right of +2. That means that z has a large probability of taking values between like a -1 and +1. Much smaller probability between 1 and 2, or -1 and -2, and very little probability of taking any value outside of 3, even though there theoretically is some probability of taking values greater than +3 or less than -3. Now it can be shown that the moment generating function of this random variable is given by this, e to the t squared over 2, that the mean of this random variable is 0, and that the variance and standard deviation are equal to 1. Okay? So these two numbers here are important to remember. Standard normal distribution means mean 0, standard deviation and variance equal to 1. Now the CDF of a standard normal distribution is defined to be the probability that z is less than or equal to z, and we calculate that according to the definition of the CDF. Integrate the PDF from -infinity up to z. Now this CDF is given a special name, and that's a capital phi of z. Evaluating this definite integral is not a trivial matter. The exercises give one way to do it. You could also approximate this definite integral using something like the trapezoid rule from calculus. But we also give values of this CDF in table C1, which is in the appendix. And down here I've given you a portion of this. Now this table is broken into two parts. There's one table for negative values of z and another table for positive values of z. But you see the title, Standard Normal Distribution, phi of z is the probability that z is less than or equal to z. Over here the leftmost column gives you the first two the ones in the tens digit, or the tenths digit of z, and then the top row gives you the hundredth digit of z. Now using this table requires the use of two important properties that are true for any random variable. Number one, the probability that z is greater than or equal to z is 1 minus the probability that z is less than or equal to z. These are just complementary events. And in terms of the CDF, this is 1 minus phi of z. Second property, the probability that z is between a and b is going to be a phi of b minus phi of a. You can think of this as this probability is the area underneath the density curve between a and b. This right here gives you the area to the left of b. This gives you the area to the left of a. If you subtract those two, then you get the area between a and b. So to illustrate use of this table, we're going to look at calculating three different probabilities. And so here I've given you a portion of the table C1 from the appendix. So let's start off with the simplest type of probability. Find the probability that z is less than 2.05, which is by definition phi of 2.05. And so to find this value, we go on the table C1 to 2.0, and then to the column 0.05, and we get the area under the bell curve to the left of 2.05 to be 0.9798. So that's all there is to finding that probability. No calculations necessary, just look it up from the table. Let's look at the probability that z is greater than negative 1.23, which is, by the first property we just listed, 1 minus phi of negative 1.23. So we go to a table C1, look up negative 1.2 over to column 0.03, and that gives us phi of negative 1.23. We subtract that from 1, and we get our probability 0.8907. Last one, let's find the probability that z is between a negative 2.65 and positive 0.23. So this is going to be phi of 0.23 minus phi of negative 2.65. So we go on our table C1 to 2.203, and we get that value, 0.5910. And then we go to negative 2.605. We get that area to be 0.0040. Subtract the 2, and we get our probability of 0.5870. Now we're going to define the more general normal distribution. So a continuous random variable x has a normal distribution if its PDF is given by this rather nasty looking function. Again, for x between negative infinity and positive infinity. Now in this PDF we have two parameters, mu and sigma. Mu is any real number and sigma is some positive number. Again, this pi here is the number 3.14. And notice here that we don't use the random variable z. We reserve z for a standard normal distribution. This is the more general normal distribution. Now the phrase x is n of mu comma sigma squared means that x has a normal distribution with parameters mu and sigma. Now notice that this second number inside the parentheses is not just sigma, it's sigma squared. That's going to be very important to remember. Now it can be shown that the mean of a normal distribution is mu, the variance is sigma squared, and the moment generating function is given by this, where exp means e raised to this power. Now the parameters mu and sigma, the mean and standard deviation, tell us a lot about the shape of the PDF or the density curve for a normal distribution. So here's density curves for random variables with normal distributions and different values of mu and sigma. We see that they all have a bell curve shape, kind of like the standard normal distribution. But notice here in this one, mean is 5, and 5 is at the high point of the bell curve. This one likewise has mean 5. That's right in the middle. This has mean 10. 10 is right in the middle. And this one also has mean 10. That's right in the middle. Okay, so we see that the bell curve is symmetric with respect to the line x equals mu. Okay? We see that mu, as mu increases, the bell curve simply shifts to the right. If we compare this bell curve here to this bell curve here, see that they're very similar shapes. Just this one is shifted. This one over here is shifted to the right. And now the standard deviation sigma, that tells you how wide the or narrow the bell curve is. If you look at these two bell curves right here, they both have standard deviation of 1 and they're fairly wide. This one here has a standard deviation of 1.5. It's a much wider bell curve. This one here is a standard deviation of 0.05. It's much taller and narrower. So what that indicates here is that this random variable has a high probability of taking values close to 10, but very small probability of being close to 8 or 12. This one here has a high probability of taking on values like between 3 and 7. Not much probability of being less than 3 or greater than 7, or at least a much smaller probability. This one here has a high probability of being between about 0.4 and 6, much smaller probability of being greater than 6 or less than 4. So again, the point here is that the mean and standard deviation, mu and sigma, tell you a lot about the shape of the density curve. Now, standard normal distribution satisfies what we call the empirical rule, and you'll be asked to verify this in the homework. But this empirical rule says three things. Number one, the probability that x is between mu minus sigma and mu plus sigma is about 0.68. And illustrated down here, here's the range of mu minus sigma up to mu plus sigma. There's about 68% of the area of our bell curve is right here in this region. Second probability says the probability that x is between mu minus 2 sigma and mu plus 2 sigma is about 0.95. So here's the number mu minus 2 sigma and mu plus 2 sigma. The second part says that about 95% of the area of our bell curve is right here in this region. And the last one says the probability x is between mu minus 3 sigma and mu plus 3 sigma is about 0.997. So about 99.7% of our area is here between mu minus 3 sigma and mu plus 3 sigma. In more practical terms, what this rule says is that if we have a whole bunch of observed values of x, about 68% of them will be between mu minus sigma and mu plus sigma. About 95% will be here in this range, mu minus 2 sigma, mu plus 2 sigma, and virtually all of them, or about 99.7% of them, will be between mu minus 3 sigma and mu plus 3 sigma. Next, we give a theorem that relates the standard normal distribution to the more general normal distribution, and which says that if x has a normal distribution with mean mu and variance sigma squared, then the random variable z, which equals mu minus or x minus mu divided by sigma, has a standard normal distribution. This right here is going to be the symbol for a standard normal distribution, normal with mean 0, a variance of 1. So it's saying if we transform this normal distribution by subtracting mu and dividing by sigma, then we get a standard normal distribution. This is a very important theorem and has a very important application. Say we want to calculate the probability that x is less than or equal to x. Well, inside of this parenthesis, we could subtract mu from both sides and divide both sides by sigma, and we get this probability right here. Well, this random variable right here has a standard normal distribution. This over here is some number. X is a given number, mu and sigma are numbers, so this is a number. That number there we give a special name to. We call it the z-score of x. We define that to be z equals x minus mu divided by sigma. And so what we can do is say, well, the probability that x is less than or equal to x is equal to the probability that z is less than or equal to z. Well, then I can easily find this probability using table C1, and just like we did in the previous example. Okay. So let's do a simple example of an application of this. Consider the random experiment of choosing a woman at random and measuring her height. Let's let the random variable x denote the height in inches, and we're going to assume that x has a normal distribution with mean 63.6 and variance 2.5 squared. Based on that assumption, find the probability of selecting a woman who is between 60 and 62 inches tall. So in mathematical notation, we want to know the probability that x is between 60 and 62. And so what we're going to do is convert both of these numbers, 60 and 62, over to z-scores by subtracting the mean from each one and dividing by 2.5, the standard deviation. So that gives us z-scores of negative 1.44 and negative 0.64. So then the probability that we want is equal to the probability that z is between a negative 1.44 and negative 0.64, which by using arguments from the previous example is equal to this, and then we look up those values from table C1 and we get our final probability, 0.8162. Lastly, let's talk about how we can do some of these calculations on our calculator. The formula for the normal CDF is built into the calculator, as is a formula for a generic normal CDF that'll work for a standard normal distribution as well as a non-standard normal distribution. To access this function, press the second key and then the vars key, and that will take you to this distribution menu, which has two submenus, distr and draw. Choose the first submenu, distr, and then the second option is for the normal CDF. Formula for the normal PDF is also built in, but that's not terribly useful, so we'll just talk about the CDF. Now, the syntax for this formula looks like this. If our random variable x is normally distributed with mean mu and variance sigma squared, well then the probability that x is between a and b in calculator ease looks like this. Normal CDF of a, comma b, comma mu, comma sigma. Now notice here that in the calculator we're going to enter sigma, the standard deviation, not sigma squared, the variance. In the book and in theoretical calculations we often talk about the variance, but the calculator always wants to talk about the standard deviation. So this last number we enter is the standard deviation, not the variance. Keep that in mind. So to illustrate how to use this, let's look back at example 342, where we had this random variable x, meaning the height of a randomly selected woman. It's normally distributed with a mean of 63.6 and a variance of 2.5 squared. Now in that example we found the probability that x is between 60 and 62, and we did that by converting things to z-scores and then looking things up on the table. We don't have to do all that on the calculator. We can enter this syntax. Select the normal CDF. Here's a, that's our lower bound, comma b, that's our upper bound, and then the mean 63.6, comma the standard deviation 2.5. Now again, notice that's 2.5, not 2.5 squared. So if you enter that, hit enter, it gives you your probability of 0.1862. Now when we do these calculations on the calculator, it may be a little bit different. The results may be a little bit different than if we were to do things by hand and convert things to z-scores just because of rounding. And that's okay. As long as it's just rounding errors, we're not going to be worried about that. Let's do another example. Let's suppose that we wanted to calculate the probability that x is less than 63. Now this is not a calculation that we did in this example, but let's just do this to illustrate a point. Notice that here in this probability we only have an upper bound on x, we don't have a lower bound. And so in order to use our calculator we need a lower bound. So here's what we're going to do. We're going to put a really small number as a lower bound. Here we're going to choose a lower bound of negative 100. Nothing magical about the number negative 100. But our height are never going to get down to negative 100, so that really doesn't restrict anything. So this probability here is approximately equal to the probability that x is between negative 100 and positive 63. And so now we have a lower bound and an upper bound, and we can enter that into our calculator. Here's our lower bound, negative 100. Here's our upper bound, 63. Here's our mean. Here's our standard deviation. Those haven't changed. You hit enter, and you get your probability 0.405. Now one last example. Suppose we want to find the probability that x is greater than 55. Well, here we have a lower bound on x, but we don't have an upper bound. And so we're going to solve that by just putting in an upper bound of a really big number. So here I'm going to put an upper bound of 200. Now height is never going to get as big as 200, so again this doesn't really restrict anything. So this probability here is approximately equal to this probability. Technically not exactly the same, but for all practical purposes they are the same. And so now we can enter that into the calculator. Here's our lower bound, here's our upper bound, here's our mean, here's our standard deviation. We hit enter, and we get our probability. So in these two examples where we don't have a lower bound or an upper bound, we just simply Make up one. That's not really going to restrict any things. Enter things into calculator, and we're all done. So on any of these homework problems, feel free to use your calculator to calculate these normal probabilities. Now the answers in the back of the book were all calculated by hand by converting things over to z-scores and then using the table. So if your answer from the calculator doesn't match the answer in the back of the book exactly, that's okay. It's probably just a rounding difference between my hand calculations and the calculator.